Welcome to lecture 21 on essentials of topology. In this lecture, we will study the concept of product topology. This is another way for creation of topology by using the given topologies. The actual idea is if we are having two topological spaces x1 tau 1 and x2 tau 2, question is what topology we can put on Cartesian product of x1 and x2. Answer is we can put a number of topologies here. At least two are well known, that is discrete topology and indiscrete topology. But our interest is to put a topology here by using these two topologies, that is tau 1 and tau 2. One of the natural answer may be when we are talking about the Cartesian product of sets, why not let us take the collection of Cartesian product of open sets, that is Cartesian product of G1 and G2, where G1 is from topology tau 1 and G2 is from topology tau 2. But the problem is here that it may not be a topology, because if we are taking two sets in this collection, let us take the first one is G1 cross G2 and second one is H1 cross H2. The problem is if we are taking their union, that is G1 cross G2 union H1 cross H2, it may not belongs to this collection because it may not be expressed in the form of G cross H, where G belongs to tau 1 and H belongs to tau 2. Let us try to understand this concept by using a diagram. This one is for set x1 and this is for set x2. If we are taking the Cartesian product of G1 and G2, let us take that this is a subset G1 of x1 and correspondingly this is for a subset of x2. Let us take another Cartesian product, that is Cartesian product of h1 and h2. So this is a subset h1 of x1 and this is for a subset h2 of x2. From this diagram, it is clear that the union of G1 cross G2 and H1 cross H2 may not be expressed in the form of some G cross H, that is Cartesian product of two sets G and H, where G is from topology tau 1 and H is from the topology tau 2. So now question is how to construct the topology on Cartesian product of x1 and x2. Interestingly, the collection will form a basis for some topology on Cartesian product of x1 and x2. Let us see it. If we are having two topological spaces x1 tau 1 and x2 tau 2, take this collection, that is G1 cross G2, where G1 belongs to tau 1 and G2 belongs to tau 2. We can show that this is a basis for a topology, and the topology which we will obtain, that topology is known as product topology on x1 cross x2. Let us see that is it a basis. The first one, this is clear from the definition itself that x1 cross x2 will belongs to this P, as x1 always belongs to this tau 1 and x2 always belongs to tau 2, and therefore Cartesian product of x1 and x2 can be written as union of some members of basis. Coming to the second requirement, let us take some B1 as G1 cross G2 from this B and also take B2 as H1 cross H2 from this P. What actually we have to justify that? If we are taking this B1 intersection B2, that is Cartesian product of G1 and G2 intersection Cartesian product of H1 and H2. And let us take an element of this B1 intersection B2, our motive is to search a B3 in B such that xy belongs to B3 is subset of this B1 intersection B2. Question is how to find out this B3. Now, as xy belongs to G1 cross G2 intersection H1 cross H2, from here we can conclude that xy belongs to G1 cross G2 and this xy is also a member of H1 cross H2. Or we can say that x belongs to G1, y belongs to G2 and this x belongs to H1 and y belongs to H2. From here we can also conclude that x belongs to G1 intersection H1 and y belongs to G2 intersection H2. What about this G1 intersection H1 and G2 intersection H2? Note that G1 is from tau 1, G2 is from tau 2, also H1 is from tau 1 and H2 is from tau 2. So from here we can conclude that this G1 intersection H1 belongs to tau 1. Similarly, this G2 intersection H2 belongs to tau 2. And if this is the case, we can also write xy belongs to G1 intersection H1 Cartesian product with G2 intersection H2. Let us take this as B3 because now this B3 belongs to B. As G1 intersection H1 is from tau 1 and G2 intersection H2 is from tau 2. Only one thing or only one step remains, that is to justify that B3 is a subset of G1 cross G2 intersection H1 cross H2. And this can be justified easily. For example, if we are taking any PQ in this B3 and that B3 is nothing but G1 intersection H1 cross G2 intersection H2, then P belongs to G1 intersection H1 and Q belongs to G2 intersection H2. From here, we can write that P is a member of G1 and P is also a member of H1 and Q is a member of G2 and Q is a member of H2. Or we can write that PQ is a member of G1 cross G2 and PQ is also a member of H1 cross H2. And if we are clubbing these two, we can conclude that this PQ is a member of G1 cross G2 intersection H1 cross H2 and that is nothing but B1 intersection B2. So we have proven both the criteria that should be satisfied for a basis and therefore the collection which we have taken as a Cartesian product of open sets for a basis for some topology and that topology is product topology. But from here one thing is clear, if we look the structure of basis, we always look for a smaller structure than the topology. But the basis which we are constructing here, that is derived from topologies and that has some bigger structure. Question comes, can we reduce the size of this P? Answer is yes, and the answer is given by this result that if we are having two topological spaces x1 tau 1 and x2 tau 2, where this B1 is a basis for x1 tau 1 and B2 is a basis for x2 tau 2, then we can construct a basis, that is B, which is Cartesian product of B1 and B2. B1 is a member of basis for topology tau 1 and B2 is a member of basis for topology tau 2 is a basis for the product topology which we have seen. Let us try to justify this result. In order to justify this result, let us take that this is tau This is the product topology on x1 cross x2. Now we are taking any g in this tau and take any member of this g. What we have to justify? We have to justify that there exists some b in this B such that xy belongs to B and that is subset of G. So our motive is to justify this point. Question is how to justify. Let us see. If we are taking this xy in G, because we have already shown that there is a basis for the product topology and that basis provide an element G1 cross G2 such that xy belongs to G1 cross G2 and that is subset of G. And note that this G1 is a member of topology tau1 and G2 is a member of this topology tau2. From here, it is clear that X belongs to G1 and obviously this G1 is from tau1 and Y belongs to G2 and note that this G2 belongs to tau2. But we already have basis for tau1 and tau2. From there, we can conclude that there exists B1 in the basis for topology tau1 and remember B2 from the in the basis for topology tau2 such that X belongs to this B1 that is subset of G1 and Y belongs to B2 that is subset of G2, or we can say that XY belongs to B1 cross B2 that is subset of G1 cross G2. But note that what is G1 cross G2? That itself is a subset of G. So what we have obtained, that is this ordered pair XY belongs to B1 cross B2 and that is subset of G. And note that this B1 is in B1 and this B2 is from this B2. And thus this collection B which is given here is a basis for product topology on x1 cross x2. Let us construct some examples. So the first and simplest example is if we are taking two topological spaces x1 tau1 and x2 tau2. Let us take that this is in discrete topology and similarly the second topology is also in discrete. What about product topology on x1 cross x2? Is it also in discrete? Answer is yes. This will also be an in discrete topology. Why? Because if we are looking the basis structure for this tau1, so this is the basis for tau1 and this is a basis for tau2. And if we are constructing a basis for this topology, that will be nothing but x1 cross x2. And what is our x1? That is x1 is from tau1 and x2 is from tau2. And the topology generated by this B is nothing but an indiscrete topology. We can also conclude that the product of indiscrete topologies is also indiscrete. Similar to this one, why not discuss about discrete topology? Let us take two topological spaces x1 tau1 and x2 tau2, where tau1 and tau2 both are discrete. Question is whether this product topology is discrete. Answer is yes. This will also be a discrete topology. How? The basis for this topology tau1, we already know that if this is discrete, that will be collection of singleton subsets. x1 belongs to x1. Similarly, the basis for topology tau2 is given by collection of the singleton sets x2, x2 belongs to x2. Question is, what about the basis for this topology? From B1 and B2, we can construct a basis for this topology, that is the Cartesian product of all singleton sets, and that will be given by Again, a singleton set consisting of ordered pair where x1 belongs to x1 and x2 belongs to x2. As this is collection of singleton subsets of x1 cross x2, the topology generated by this basis will be discrete topology. Our final conclusion is that product of two discrete topological spaces is discrete. Let us take some more general examples, beginning with Euclidean topology on set of reals. Let us take the product of Euclidean topology with itself. Question is, what about the basis for product topology on R2? Answer is, if we are looking or if we are recalling the basis structure for Euclidean topology, we have seen that the open intervals for basis for Euclidean topology. So this will be if an interval AB, and similarly if here is in the interval CD. So the basis for product topology on R2, that will be given by open rectangle, and that will look like in this form. Moving to another example, let us try to see the basis for product topology on R2 when the topologies are lower limit topology on R. So the basis element can be visualized by using this figure, because we know that the basis elements for this lower limit topology looks like in this way. They are semi-open interval. Similarly, we are taking another semi-open interval for this lower limit topology, that is this CD. So how this basis element will look like? This will look like in this way. This will be closed from lower side. This will also be closed from this left side, but this will be open from upper side and open from right side. So finally, this is a basis element for the product topology on R2, where R is endowed with lower limit topology. So finally, this is an image of a basis element for the product topology on R2 when lower limit topologies are with set of real numbers. Moving ahead, we have already seen the basis. Actually, we have seen two bases for product topology. Let us try to reduce the size further by using the concept of subbasis. Actually, this concept is based on the notion of two maps, phi1 as well as phi2, and these maps are called projection maps. From the definition, this is clear that phi1 is a map from x1 cross x2 to x1, and phi2 is also a map from x1 cross x2 to x2, and these maps are defined like phi1 of xy. This is sending each ordered pair to x, that is in first component x1, and phi2 of xy is equal to y. From definitions from definition, we have some observation. The first one is that both the maps, that is pi1 and pi2, are surjective map. Also, if we are taking a subset G1 of x1 and we compute this inverse image of G1 under pi1, that will be collection of all xy in R. This is collection of, let us take all ordered pair x1 x2 such that pi1 x1 x2, this belongs to G1, or this can be written as, this is collection of all ordered pair x1 x2 such that pi1 x1 x2 is nothing but this is x1 belongs to G1, and from here we can write that this set is nothing but G1 cross x2. Similarly, if we are taking a subset G2 of x2 and we are computing pi2 inverse G2, that can be written as x1 cos G2. With these concepts, let us move ahead, but let us see one more interesting thing. about the intersection of this phi 1 inverse G1 and phi 2 inverse G2. The intersection of these two, that is phi 1 inverse G1, which we have already seen that this is G1 cross X2. Note that G1 is a subset of X1, and phi 2 inverse G2, that is given as X1 cross G2, where G2 is subset of X2. So let us take this. This is for set X1 and this is for set X2. Also, this region is representing set G1 cross X1, and if this is, sorry, this is G1 cross X2. If this is representing G1 cross X2, actually this is our set G1. Similarly, let us take in the region, and this region is representing G2 cross or X1 cross G2. So actually this is a subset G2 of X2. From this diagram, this is clear that the intersection of these two is this particular region, and this region is nothing but G1 cross G2. Now, having this idea in mind, let us see that how a set becomes a sub-basis for product topology. Actually, the set is given by union of two collections, that is two sets. First one is phi 1 inverse G1, where G1 belongs to tau 1, and phi 2 inverse G2, where G2 belongs to tau 2. If we are taking this collection as P dash, we can justify that this P dash is sub-basis for the product topology on X1 cross X2. Let us have a glimpse on X1 cross X2. Let us denote by tau the product topology on X1 cross X2. Also, let us denote by tau dash the topology generated by this B dash. Our motive is to justify that this tau and tau dash both will be same. So what we have to justify that this tau dash is coarser than tau, and also justify that tau is coarser than tau dash. If we are looking for this inclusion, and if we are taking any g belongs to this tau dash, what about this g? G will be nothing but union of finite intersection of member of members of B dash. And note that how the members of B dash will look like. They will be of the sum form, that is G1 cross X2 and X1 cross G2. We have already seen that these are also member of this basis for product topology, and therefore they will also belongs to tau. And if they are in tau, by the feature of or by the definition of topology, union of their finite intersection will be a member of tau, and therefore this G will belongs to tau, and it justifies that this tau dash is coarser than tau. If we want to justify that tau is coarser than tau dash, as we know that this G1 cross G2, such type of Cartesian products are member of basis for the product topology. But note that what we have seen on the previous slide, that this G1 cross G2 is nothing but this is the intersection of phi 1 inverse G1 intersection phi 2 inverse G2. And note that this pi 1 inverse G1 and pi 2 inverse G2, they are member from B dash, and therefore they will be the member for basis for this topology, that is tau dash, and therefore this G1 cross G2 will be a member for basis for topology tau dash, and therefore this topology tau will be coarser than tau dash, and hence this P dash is a subbasis for product topology. Moving ahead, we have seen two concepts for creation of new topology. One is the concept of products and second is the concept of subspaces. Let us try to think about some relationship between these two concepts. The relationship is stated as under: if we are having two topological spaces x1 tau 1 and x2 tau 2, and let us take subspaces A1 with relative topology on it and A2 with relative topology on it. It means that we are taking A1 as a subset of x1 and A2 as a subset of x2. But the conclusion is that if we are trying to find out the product topology on Cartesian product of A1 and A2, as the topology are already given on A1 as well as A2, this product topology is same as the subspace topology on A1 cross A2 as a subset of x1 cross x2. Let us try to justify, or let us try to see this result. Note that when we are talking about this A1 with relative topology on it, this relative topology will be given as something like this is A1 intersection G1, where G1 belongs to topology tau 1. Similarly, whenever we are looking for this subspace, that is A2 tau to A2, here this topology is given as A2 intersection G2, where G2 belongs to tau 2. Now if we are trying to find out the product topology on A1 cross A2, the basis for this topology, let us take this is some B that will be given by the Cartesian product of members of these topologies, that is A1 intersection G1 Cartesian product with A2 intersection G2, where G1 belongs to tau 1 and G2 belongs to tau 2. Now coming to the next, when we are considering this A1 cross A2 as a subset of x1 cross x2. Note that x1 cross x2 is endowed with product topology. So the basis for relative topology on A1 cross A2, let us take that this is B star and this is given by A1 cross A2 intersection G1 cross G2, where G1 belongs to tau 1 and G2 belongs to tau 2. And we are taking intersection with G1 cross G2 because we know that such collections G1 cross G2, where G1 belongs to tau 1 and G2 belongs to tau 2, is a basis for product topology on x1 cross x2. So what we have got? We have got two topologies on Cartesian product of A1 and A2 with their basis. One basis is given by B and another basis is given by B star. But interestingly, both sets will be equal. That is what we can justify that A1 intersection G1 Cartesian product with A2 intersection G2 is same as Cartesian product of A1 and A2 intersection G1 cross G2. If we want to justify it, let us take some element PQ in this A1 intersection G1 Cartesian product A2 intersection G2. So from here, we can conclude that P belongs to this A1 intersection G1 and Q belongs to this A2 intersection G2, or P belongs to A1 and P belongs to G1. Also, Q belongs to A2 and Q belongs to G2. From here, we can write that PQ belongs to A1 cross A2 and this ordered pair PQ also belongs to G1 cross G2. Or we can conclude that this PQ belongs to A1 cross A2 intersection G1 cross G2. So actually this is a subset of this one. And similarly, we can go in the reverse direction and we can justify that this is a subset of this one. It means that this P and B star both are same, and that's the justification about this result, that the product topology on A1 cross A2 is same as the subspace topology on A1 cross A2 when A1 cross A2 is considered as a subset of X1 cross X2. These are the references. That's all from this lecture. Thank you.